Okay, here's a question from Jun14. Okay, first thing we see is that we've got constant accelerations. So that means this is going to be probably a suvat question, okay? The thing about this question is there are two particles, A and B. I've got the accelerations of each one, so I'll turn those into column vectors, and I've got the initial velocities. This is the velocity when it leaves, this is the velocity of B when it leaves, so I've got accelerations, I've got initial velocities, so I can already begin to fill in the suvat for A and for B. Okay, with those. What I do have to pick up on later is the fact that A starts from the origin, so that means that the S I get for A is going to straightforwardly be its coordinates where it is, whereas the S I get for B will be its displacement from its starting position, so I'm going to need to make an adjustment to find out where B is. I don't need that for part A. For part A, this is just 10 seconds after it leaves the origin. I need the position vector of A. Okay. Now, as we said, the displacement of A, because it starts from the origin, will give us its position vector. So I've got I've got A. I know for this part of the question, T is 10. So if I substitute T equals 10 into S equals UT plus half AT squared. So that's what I'm doing here. I'm doing the position vector of A. The displacement of A equals its position vector, equals UT plus half AT squared. So I've got the UT, the U times the time. Actually, I can put in the time is 10. So 4/2 times 10 plus half times the acceleration. There's the acceleration. Half times a minus 0.40 times 10 squared. So I just have to work all of that out. So the first thing multiplying by the 10 is going to give me 40/20, and I'm adding on half of that acceleration is minus 0.2, and I'm multiplying by 100, so that is going to be plus minus 20 naught, which is going to give us 20 as the position vector. And that is exactly what I was asked for. I was asked for the position vector. That is the position vector of A, and I can stop there. But then I've got to show that the two particles collide. That means that they're in the same space at the same time, and I need to find the position vector of the point where they collide. Okay, so this is to do with where the particles are, so I need to find the position vector of each one. Now for A, this thing here, except going back to T's instead of the 10s, that will work for me. But for B, the position vector I get is all very well, but it's the displacement I get is all very well, but its position vector is initially 11.2. Back up here in the question, okay. B starts already at the point 11.2i. So B is starting from this point on the x-axis. So if B starts here, and then I've got some kind of displacement S from that position, the actual coordinates here will be the initial position of B plus the displacement. So I'm going to use R for position vectors, okay. So RA, okay, is A starts from the origin, so it's basically just what I did before, 4/2 times T, I don't know what T is now, plus a half times the acceleration, minus 0.40 times T squared. So that's my position vector of A. My position vector of B is going to be its initial position, that was 11.20, okay, plus SB. So this is where it started, and this is its displacement from where it started. And I'm going to use the same equation for SB as I did for SA, UT plus half AT squared. So this is 11.20 plus initial velocity times T. B's initial velocity is this one here, 0.4, 0.6, plus a half times B's acceleration, 0.2, times T squared. So now I've got two positions, one for A and one for B. Now these particles are supposed to be colliding. So if they collide, it means they've got the same position vector. So we'll just simplify both of these. So A's one simplifies to 4T, and then a half times minus 0.4 is minus 0.2T squared here. And in the other bit, it's just 2T, and this one's 0, which is quite nice. Okay, and then RB is the whole of this simplified. So at the top, I've got 11.2 okay, plus 0.4t. And on the bottom, I've got 0 plus 0.6t plus a half of 0.2 is 0.1 t squared. So these two vectors have to equal each other. So I could either equate the x's or equate the y's. I can see I've got an easier quadratic if I equate the y's, but since you're allowed to use your calculator to solve the quadratic, it doesn't really matter what you equate. So in fact, if we say if they're the same, then let's do the x's. 4t minus 0.2t squared equals 11.2 plus 0.4t, which simplifies into the quadratic 0 equals, okay, on the other side I'm going to have 0.2t squared. I'm going to have 0.4t taking away the 4t, so that's minus 3.6t, and I've got the plus 11.2. Okay, all I've done there is I've got 0 on the left-hand side, and I've taken this away, and I've added that, and I've got this quadratic, which without a calculator might be a bit tedious, but your calculator in menu A will just let you solve it. So I hope you can see I've entered the coefficients there, and it gives me the first solution is 14, it's x1, and it tells me x2 is 4. So my two times are 14 and 4. Okay, well, very often we can eliminate one of the solutions of our quadratic completely, but here I don't know which of these is correct. They might both be correct. I got these by saying that the x parts were the same. So the x line of the coordinates are going to be the same with as the two particles, but that doesn't guarantee the y coordinates are the same. So if I plug 4 into 2t, I get 8. But if I plug it into 0.6t plus 0.1t squared, I'm not sure I am going to get 8, so I'll have to try that out. So I've plugged 4 in on my calculator, and I get that the y-coordinate of b at that time is 4, which is not the same as for x. So it appears by trying that out that 4 is not the time I want, so therefore the one I do want is 14. So I should really check that does work. So when t is 14, I can see the y-coordinate of A is 28. So I need to check that with t equals 14, I get 28 from this one. So on the calculator, this is the same calculation as before, but with 14s instead of 4s. And this time I do get 28, so I know that 14 is the correct time. So let's go back and see what the question actually asks me. Okay, show the two particles collide and find the position vector of the point where they collide. Well, I've just done that. So what I've done, well, I've done it for the y-coordinates. I've said when t equals 14, okay, RA, we've just worked out RA, we just checked the y-coordinate was 28. Now, the x-coordinate I used to set up this equation, so I know they're going to agree, but I haven't worked that out yet. So let's work out the x-coordinate of A, which is this 4t times minus 0.2t squared. Put 14 in for that. Here we go, and we get an answer of 85 over 4, 16.8. So RA equals this, and if I substitute 14 into this other equation, then I will get the same answer for RB. And the fact that I've got the correct answer for the 16.828, because they are the same, all I need to do is say, therefore they collide at, and the coordinates of the point where they collide are what I've just found, 16.8, 28. And that's convincing enough. I've got solved a quadratic, I've got the right coordinates. It's in my interest to check both ways that I've got the same vector both times, but that is the correct point, so I finished the question. Better just check the wording. What did it ask me to find? It asked me to find the position vector of the point. So I've politely given this as coordinates, but actually they want the position vector, so I should really give that column vector, which I've already done here, but 16.828 is better because they want a column vector. Okay, finished.